Okay, so thanks so much for asking me to discuss the paper. I learned a lot. The slides will be available on the Discourse website, hopefully by tonight. So I'm going to skip the first slide. It's just the motivation that Stavros talked about. Essentially, can cash flows that are co-integrated have very different present values, right? And I worked with co-integration before, so my intuition comes from standard Lucas economy, exchange economies, and this is what I would call the canonical model of co-integrated cash flows. So consumption is just a random walk in logs, and then dividends are subject to two shocks, the consumption shock and orthogonal shock, and then they have this co-integration term, right? So if dividends are higher than consumption, the trend is the growth rate is negative, and dividend will converge back to consumption. And let's say we have a pricing kernel that prices both risks, not just the consumption risk E, but also the orthogonal dividend risk U. So it's a multi-factor model. And then if you go through the algebra and you solve for risk premia, well, the consumption risk premium is the standard term, the risk aversion, right, times the volatility of consumption. And the dividend risk premium depends on the same consumption risk premium, but it also has this U term in it, this other risk factor. But note that the risk premium is multiplied by phi to the n minus 1, power of n minus 1. So as n goes to infinity, phi to the nth power goes to 0. So in the limit for very long consumption claims, the risk premium will be identical to those of consumption. So in this model, you will not be able to create this wedge between the present value of consumption and the present value of dividends, right? So this model will not work, right? And I think my intuition and probably most people's intuition are sort of along these lines. So I'm used to these sort of models in discrete time. My continuous time skills have diminished, as depreciated quite a bit since grad school. So part of my discussion will be sort of my path to the intuition of what's going on in this model, okay? So will be a very geeky discussion for a very geeky paper, at least for the first half. So, one more thing. I haven't thought this through, but if you allow for leverage, then you can, where the dividend claim is levered with the consumption shock, this might work. So something that I want to spend some more time on and see whether this extension might work and generate this wedge. So here's the, oops. How do I get back? There we go. So the model in the paper is a production economy in continuous time, has some standard assumptions. So consumption is, again, a random walk, just like in my example. And then we have, in this version, just two assets, the consumption claim plus some other shock. So it's, again, it's a multi-factor model. And then we have this fund that sort of gets mean returns μx from these two assets and pays out x, right? This is the evolution of the value of the fund, totally standard. So the paper is all about the assumptions about this payout process x. So the question is there a payout process that is co-integrated in logs with consumption, but the present value is finite if the present value of consumption is infinite. That's the name of the game in the paper. So here are the results, and I want to sort of go through the simplified math the way I understand it to develop some intuition. So the first result is, as Stavros pointed out, that the state variable, the log wealth minus consumption, is stationary. Okay? Actually, did I miss a slide here? No, I didn't. there, that's the slide I was missing. So it's all about this payoff process X. So the state variable here is this log value to consumption ratio. So the intuition, if dividends, if the value of the fund is high, then you pay a lot. If it's low, you pay out less. And the key thing is this functional form, is that this dividend yield, this payoff yield, is the maximum of a affine function of z and epsilon, where epsilon is positive. So the key thing here is the kink, and I will come back to that. So an alternative might be, and to me it's more natural to assume that the log payout to value ratio is affine. So I'll come back to that at the end, okay? So in terms of the intuition, this z state variable involves this endogenous variable w, so it makes it a little harder to get the intuition because you don't have this exogenous state variable, okay? So the key part, or the key properties to get this wedge between these present values are the properties of z, in particular the role of this kink, okay? And I want to walk you through it, at least the way I understand it. So here's how the proof goes logically. So the first step is pretty straightforward. The wealth consumption, or the value consumption ratio is stationary. Consumption is a random walk. Therefore, you have mean reversion in W, right? If W is high compared to consumption, it's going to come down, standard. That means there's a stationary distribution, and that's a combination of an exponential and the normal, which is due to this kink, okay? I will show you the distribution later on. You can get it in closed form. Then the next step is to show that the payout to consumption ratio is also stationary, okay? It means, again, consumption is a random walk, so you have mean reversion in X, okay? So here's now the key part. If we want to price the present values, you can show that the end period zero coupon strip of payouts X is related to the present value of the consumption strip plus this extra term in orange. And this extra term in orange, that's the key term. Now it's a pretty complicated object, as you can see, okay? F is this exponential of the maximum function, but the key thing is you want to look at this, the properties of this orange highlighted object. And the key part in the paper, the key result, is that there are parameters where this term actually goes to minus infinity, right? And that will then drive this wedge. So you have a finite zero coupon X claim, and then you have, on the right-hand side, you have two infinite terms, and if you do the asymptotics correct, they will just offset. So the key thing is that this term here has some really weird properties. Now, the intuition would be z is stationary, therefore the exponent of z is also stationary. So this is a function of stationary objects, so this limit should be finite. That intuition is wrong, okay? And part of my took me a little while to understand why that's the case, and I want to spend the next few minutes on developing this intuition, okay? So the key thing is, so first we went from the P measure to the risk-neutral Q measure. Then we're going to do another change of measure to this Q tilde measure, okay? So then the paper shows that there are parameters so that even though Z is stationary under P, Z is non-stationary under Q, or Q tilde. That's the key part, the technical part in this proof. So what this implies, or in this case, this implies that under Q tilde, Z converges to minus infinity, okay? So it doesn't have a stationary distribution like under P, okay? So that's the key part, and I will come back to why that is on the next slide. So let's follow the math first, okay, before we come back to this. If Z goes to minus infinity, right, F is this exponential function. It means F of Z goes to 0, right? So the max would be the epsilon, because Z is negative. and then this exponential of z, where z goes to minus infinity. So this f of z will go to 0. That means the expectation of z under the q tilde measure will also be 0. Okay? And then if we plug this now back into this orange box under the q measure, so you can see that on the right-hand side in this box, it's the log of the expectation under the q tilde measure. The expectation go to 0, so log of 0, the right term will go to minus infinity. Okay? So logically, the left-hand side is finite. The right-hand side, the orange box, goes to minus infinity. So the middle, the consumption claim, has to go to plus infinity for this to hold, right? Now, this is not quite correct. If you do the proper asymptotics, divide by n and so on, then, but that's the intuition, okay? So the key thing is that in this model, that the z is non-stationary under q tilde, while it's stationary under z. And I understand the math, but the intuition is not obvious. When you change measures, things happen, and sometimes the intuition breaks down. So the next slide will be about, how can that be? So the key is the drift of z. So the key property is that this is actually not quite true. It's a typo. Z is stationary under p and non-stationary under q and q tilde. So the implication is that z is mean reverting under p, but diverges under q and q tilde. Again, it's a typo. Okay? And the reason is that we have this kink. So you can write the drift of z to the max function. You can have two regimes. If z is high, then this is just an AR1 behavior. So the drift is just like an AR1 process. So if z is above z star, everything is totally standard AR1 type. Okay? Now, on the other side, if z is small, then this drift is not exponential, but linear. So you have slower mean reversion if this z is small. And that's the reason why the slower mean reversion is the reason why you get this non-stationarity under the q and q tilde measure. Because on the left-hand side, if z is small, the mean reversion is slower. So here's some pictures. So this is the positive part. So the impulse response function of z is just an AR1, right? Standard. The more interesting part is this one. If we have a large negative shock to z, so z is below this z star, the blue line, or the orange line, would be the symmetric AR1 impulse response function. So you converge pretty quickly to the mean. However, with the kink, the blue line, until you hit z star, mean reversion is linear. It's not like an AR1, not geometric. Okay? Only when you hit z star, then you get into the typical AR1 behavior. So you get this very slow mean reversion compared to the normal case. Now, what happens then, if you now go to the Q measure, so this picture has parameter values so that z is also stationary under the Q measure. Okay? So you get this under the Q measure, you still get mean reversion. So this is not the case we want. What Stavros wants is to have parameter values like this, where this z diverges to minus infinity. And that's exactly this slower mean reversion under p translates into this non-stationarity under q. That's the idea. So this kink is really important. Okay, 1 minute, right? So if you look at the distributions, so on the left-hand side, on the right-hand side of z star, it's normal, on the left-hand side is exponential. If you zoom in on this, you can see actually there are fatter tails on the left-hand side. So this difference, the blue line is the distribution of z, and the dashed orange line is the normal. So you have more mass on the left-hand side. So when you switch measures, this becomes a non-stationary distribution. Okay? So some comments. This is an example. I would like to know what specific assumptions drive the results, and are they more robust? Is this just a simple example, or is this a bigger problem that arises generically? So I think some more conditions on what we need to get this, this wedge in the present values would be very useful. So I also think it would be useful to look at this linear model with logs without the kink. So I think his result would not go through, but I might be wrong. That's my intuition, okay? So with that, I'm going to stop right here.